If probability questions feel like 10 different random types of questions, they're not. There's just two of them: comparison questions and independent events. Once you see that, probability finally starts making sense. My name's Farhan, I'm a junior doctor, and I've helped over 100 students get into medicine and dentistry across Australia. And today, you are going to learn how to answer both types of probability questions: the comparison-based ones with a framework, and basically everything else with one single principle. So, there's two question types when it comes to probability. The first of which is the comparison questions, and they look something like this, where you've got suppliers or manufacturers or methods that you're comparing. And that's compared based on a different number of variables. So here, it's the likelihood of on-time delivery and delivery being uncontaminated. So it's literally just comparing one thing against another. And then for the other questions, it's basically just everything else, which we'll go through. But for the time being, let's focus on the comparison ones. And for this, I'm going to introduce you to the TFS method. Basically, your one-stop shop to answer any of these comparison questions quickly and with ease. So TFS stands for table, focusing on one outcome and standardizing the numbers. So the first thing you want to do is just set yourself up a table. Now, I'll go into this in a bit when it comes to success rates, but if there's system A, there's system B, and it's based on these two different variables, then just make the table so that you can fill in the numbers and then use this table to end up answering the question. Now, when you are making this table, the second thing to do is focus on one singular outcome, either success or failure, not both. That's what I meant by success rates over here. So, essentially, for these questions, what they do is they like to present the same number from different perspectives. For example, X works 40% of the time and Y stops working 60% of the time. But you know, in truth, both of them are just 0.4 success rate. The questions typically present two factors, and one of these factors almost always is the same success rate. So there'll be the same number this way, just presented differently. Now, my personal take on this is to present everything in terms of success rate, because it allows you to interpret the table easier. Because I want to say like 99 out of 100 times, you're picking the better option. So better is going to be depicted by the likelihood of success. So present everything in like a positive format. So instead of stops working 60% of the time, write 40% of the time it will work. And lastly is to standardize the numbers. Convert them to the same form. My recommendation is decimals. So this rewards quick conversions, this question type in general. If you're not comfortable with your conversions, then go watch my video on fractions and ratios. However, the reason I'm recommending this is because they like to present the same number in different ways. 0.4, 2 out of 5, 40%. So my recommendation is to just change everything to decimals, because if you need to, not that I've ever had to, but if you need to and they make these questions harder, you'll end up needing to multiply the probabilities because of independent events. We'll go into that literally later on in the video, but decimals are your best friend here. That's all I'm going to say. So let's go through some work examples, starting off with the one that we just saw. So feel free to pause the video now and try and implement the TFS method to help answer this question. So hopefully you've had a go at this question. Let's run through it together. So the first thing is T. Set up your table. This is what it's going to look like. So let's fill it out. Supplier X successfully delivers on time. That's a success rate. That's good. With the probability of 0.8. So we're going to pop in 0.8 into the table. Now, it has a 0.15 probability of the delivery being contaminated. Now, we don't want it to be contaminated. That's a negative thing. And if you have a look at this on the actual question, it says, based on the likelihood of on-time delivery and it being uncontaminated, it's giving you the success characteristics here. So we're going to put uncontaminated delivery as our success metric. So 0.15 probability of contamination equals 0.85 probability of uncontamination. Next, supplier Y fails to deliver 20% of the time. So that's a failure rate. We want success rate. That's 80% success rate. And successfully delivers contaminated ingredients 4/5 of the time. So that's 0.8 when it comes to just a quick conversion. So if we answer the question now, yes, supplier X has a 5% higher probability of delivering uncontaminated ingredients. As you can see, with most cases with this comparison question type, there's going to be one factor that's the same between the two. So let's go on to just one more example to drive it home. Use the TFS method to answer this question. Alrighty, so let's run through it together. So set up our table as always, and the next thing that we're going to do is run through what it says. So the success rate of delivering within 24 hours is 75% for railway service. Lovely, pop that in. And road service fails to deliver within 24 hours 1/4 of the time. So let's convert that into a decimal. That's 0.25. And then let's convert that into a success rate. That's 0.75. It's the same between the two. So we know our answer is going to be dictated between the difference between these two. Anyways, let's keep going. The probability of incurring additional handling charges. Now, that's a negative thing. Why would I want to incur these additional handling charges? And again, it tells you in the question, considering only the probability of avoiding additional handling. So it tells you the success metric there. So we're going to put the success metric here, which means we're going to flip this around, and that becomes 0.7. And 0.2 for road service, flip that around, becomes 0.8. So the reason I basically like having everything in success rate and not failure rate is because you're basically just looking for the bigger number in this case. And here is the bigger number, so road service is better. So no, both services have equal 24-hour delivery rates, but road avoids charges more often is the answer to this question. So hopefully the TFS method helps you. It's just one of the many frameworks that I've got for the UCAT in general. So if you want all of my frameworks in one place, then just click the first link in the description below. Otherwise, let's move on to basically every single other probability question that can come up. And the principle that I really want you to remember is independent events. Here's what I want you to remember. The probability of two independent events happening at the same time is the probability of event A multiplied by the probability of event B. That's it. That's all you need to remember. Now, what actually is an independent event? It's basically events that have no impact on one another. For example, if I flip a coin and it lands on tails, that's event A. Whereas event B might be having eggs for breakfast. They're completely independent events, unless for some reason you choose to eat eggs whenever you land a tails on flipping a coin, at which point it becomes dependent, right? But for the most vast majority of the questions that you get in the UCAT, they're almost exclusively independent events, where one event has no bearing or impact on another event. So let's just go through an example, right? What's the probability of me getting a heads when I flip a coin? It's going to be 1/2. What's the probability of me landing on B, for example? If I had a spinner here and there was an equal probability of landing on A, B, C, and D, then the probability of that would be 1/4. And so if I was trying to find the probability of me getting heads here, so probability of heads, and then probability of landing on a B, then you multiply those two together because they're independent. So we end up getting 1/8 in this case. So what about if the probabilities change? It's going to remain the same here, so 1/2 here, but pretend like this is a beautiful, nice equilateral triangle. The probability of landing on B here is going to be 1/3. So what's it going to be for both heads and landing on B at the same time? The probability of that is going to be 1/6. You just multiply the two together. That's it when it comes to independent events, guys. Literally, that's it. The rest of probability skill comes in applying this specific skill to various different scenarios, which is exactly what we're going to go through. So let's run through some worked examples, starting off with this one. So pause the video now, have a read, have a go, and then we'll go through it together. All right, let's go through this question together now. So the point of this question is to basically just test your understanding of probability in this case, and to see if you fall into the common assumptions and the traps of thinking that just because you've got 15 times here, 15 heads, so 15 heads out of the 15 times that you flip the coin, that somehow on the 16th one, the probability is going to change. It's like a gambler's fallacy, if you will. So with that in mind, on the 16th flip, it is still going to be exactly the same because the previous flips have no effect on the outcome of the 16th flip. If you struggle to kind of conceptualize this with this amorphous letter of P, then just give it a random number. Remember, this number can be anything, really. Maybe the probability of landing on a head is 55 out of 56 times. So then when you have an outcome like this, it kind of makes sense, right? So in this case, the answer here is A. The previous flips have no effect on the outcome of the 16th flip. Okay, let's move on to our next question. Feel free to pause the video now and have a go. All right, so let's run through this one. So we've got, in the country of Albania, the population is divided into equal numbers living in apartments, houses, and cottages. So 1/3, 1/3, 1/3 into these three. Similarly, equal numbers into car, bicycle, public transport. Fantastic. So housing type and commute method are independent. There's our lovely keyword there, which means that when we need to do a multiplication, we can. So if 90 people from Albania are selected at random, then the expected number with both an apartment and a car is less than 20%. How do we do this? Well, what's the probability of someone being in an apartment? Well, we know if the population is divided into equal numbers living into apartments, houses, and cottages, then the probability is 1/3. What's the probability of someone having a car? The probability of car. Well, we know that the transport options, car, bicycle, and public transport, divided into 3 as well. So that's 1/3. So what's the probability of both of those happening at the same time? If only we had a formula for that. All we do is we multiply it. So that ends up being 1/9. So if we get this number of 1/9 and then we multiply it by the 90 people selected, then we end up getting 10. So our answer is yes, the number will be approximately 10, as housing type and commute method are uncorrelated and each fraction is 1/3. So B is our answer in this case. Let's kick on into our next question. So pause the video here and have a go. All right, so let's run through this question now. So the probability of Anna, Ben, and Chloe marking an exam is 0.2, 0.5, 0.3 respectively. And then the number of errors made by them per 100 exams is what we have here. So here, these are, you can assume them to be independent events here, because one person getting an exam to mark and then them making errors on that marking, in this case, would be independent. Maybe it is dependent in real life, but if it doesn't say so, then just assume that they're independent, unless there's one of the answers that says there's no way that we can assume that they are independent events. So anyways, let's go and assume that they are independent. And what we want to find out is basically who makes the most errors. That's the question in our mind. Is it Ben or is it someone else? So the way we do that is, well, let's just say we have the probability of getting an exam. So probability of marking an exam and then probability of error. And because these are independent, then we can multiply them both per person. So 0.2 times 35 gives us 7. And then 0.5 times 12 gives us 6. And then 0.3 times 18 gives us like 5.4, I think it is. So this is basically the, if you can think about it, the error rate by how much they mark. It's like their ratio of making the errors in this case. Now, if you really want to, you can multiply it by 800. But if you multiply everything by 800, what's going to change here? You already know who makes the most errors. It's going to be Anna, because her number here is the highest, because she makes the most errors per 100 exams, regardless of her picking up the least of the exams to actually mark. So here, the independent events of marking an exam and then making a mistake on that exam, if you multiply them, you end up getting this number. You end up getting the answer of no, the highest number of errors are made by Anna. So there you go. That's the answer to that question. Let's move on to our next question. Feel free to pause the video here and have a go. All right, let's run through this together now. So in a population, there are more left-handed people than not and more tall people than not. And these traits are independent. Is the probability that one person chosen at random is left-handed and tall greater than the probability of two people chosen at random that are both being tall? So here's what it's asking. Is the probability of someone being left-handed times tall greater than someone being tall and then another person being tall? Okay. Now, these are just letters. We don't actually know what any of these numbers are. So the the gut reaction is to go with no, as we don't know the exact proportions of each trait in the population. And so if you picked C here, then I don't blame you, because you're actually correct. But there is a better answer in this case, and that answer is A, providing that there are more left-handed people than tall people in the population. Because what it's doing is it's imposing a condition, and then only upon that condition does the answer become yes. Now, the reason I've tried to write things out in an equation format is so that you can see for yourself what it's actually meaning. So if these are the same, and providing that this is bigger, because it's saying that there are more left-handed people than tall people in the population, then yes, it does make sense that whatever this number is bigger than whatever this is. So if you're struggling with these kind of questions, I always recommend try to write it out in an equation format so you can almost see mathematically what's going on. That way, you might be able to answer a question like this without guessing and actually use the numbers and the theory of probability to get the answer correct. So the answer to this question is A in this case. Now we've got one more question, a bit of a tougher one. Feel free to pause the video now and have a go. All right, so let's run through this question together now. The question is, should I expect to be in a profit? The way we figure out if we expect to be in a profit is we figure out how much we win and we figure out how much we lose based on the probabilities. So how much do we lose? Well, there's only one payment per game. So it's £2 per game that you play. So 36 times 2 gives you 72. You've lost £72 to play these 36 games. Now the question is, well, how much do we win? So here's what we can see. I win £3 if exactly one spin lands on red. So I want you to almost try and visualize this, right? We've got spinners here and it's divided up into 6 categories. 1, 2, 3. 1, 2, 3. And there's only one red section that if you land on, then you're going to win. Now, spinning these spinners is independent. So if you spin this one on the left-hand side, let's just say that's A, then that has absolutely no impact on you landing a red or not on B. So these are independent by nature. So let's figure out what's the probability of getting exactly one to land on red. So having one to land on red looks like 2 cases where A is red and B is not, but then also we have A is not red and B is red. So what does that look like? Let's go with this one first. That's 1 over 6 times 5 over 6. And what's this one? We've got 5 over 6 for not red, for A here, and B 1 over 6 here. So if you total these up together, this ends up giving you basically a 10 on 36 chance of getting a red. So 10 times out of 36, you are going to win £3. So how much do you win? If you play 36 games, you win 3 times 10, which gives you 30. So winnings equals 30. But we've also got one more here. I win £12 if exactly 2 spinners land on red. So what's the probability of A landing on red and also B landing on red at the same time? That would be 1 on 6 times 1 on 6, or just once out of the 36 times. So out of the 36 times, you can expect to win the £12 once. So 30 plus 12. So your total winnings here are £42. You're losing 72, you're winning 42, so you cannot expect to be in a profit. So the answer here is C, no, because on average, I will win less than I pay to play. So there's your answer. It's a bit of a complicated question there. If you're able to keep up through it, then fantastic. If not, then just go through that as many times as you need until it makes sense. Because if you understand that part of probability, then the rest of probability is going to be a piece of cake. So that was just a handful of questions that we've gone through so far. And if you want to do more practice questions and you don't already have a practice platform, then you can use the code Farhan for 10% off med entry. Otherwise, let's go into one more thing, tree diagrams. Now, this is really important because they often actually get used quite a bit when it comes to probability questions. Tree diagrams are a good way to find probabilities of multiple events happening one after another. And there's two types of them: with replacement and without replacement. So here's what a with replacement graph looks like. Let's just say you've got two kinds of marbles in a box. You've got black marbles, you've got white marbles. You've got 3 black marbles and then 5 white marbles. So the probability of you reaching your hand in there, I'm just going to draw it out here, reaching your hand in here and then pulling out a black marble is going to be 3 out of 8. Now, the whole concept of a with replacement tree diagram is that once you pick the marble up, you also put it back in. So the probabilities do not change. So with that said, if we wanted to find the probability of drawing out a black marble and then a white marble, then it would look something like this. Black marble, white marble would be 15 divided by 64 as your probability. Remember, these are independent events, so you can multiply them here. Now, the wording of the questions is often where people get tripped up here, because if I ask you, find the probability of pulling a black marble and then a white marble, then yes, this would be the answer. But if I asked you, find the probability of getting a black and a white marble, then the answer actually becomes 30 over 64, because I haven't specified which order I want the black and white marble to be pulled out. So the order actually matters. If they're general and just say black and white marble and the implication is any order, you need to be able to add both of these up. So that's a tree diagram with replacement. Without replacement is where it gets a bit trickier, because this time the probabilities change. So for example, let's just say we've got green and blue marbles in our box this time. We've got 21 marbles, 12 of them are green and 9 of them are blue. So the way we draw this out is starting at the node, blue and green, and then the probability somewhere along the line. Cool. So let's follow this pathway for now. There's a 12 on 21 chance of pulling a green. So once I pull this green out of here, I do not put it back when it comes to without replacement. And that's what changes everything. That's what changes the total amount of marbles left in there. It's no longer 21, it's now 20. The number of blue marbles hasn't changed, so it's still 9, but the number of green marbles has, because we've just pulled one out. So this goes from 12 to 11. So now, if I wanted to find the probability of getting 2 green ones, it would be 12 over 21 multiplied by 11 over 21, giving us 11 over 35. Now, technically, this is a dependent event, but you still can multiply the probabilities here to find what you want at the end of the day. This is probably the only exception. Otherwise, the UCAT's just not going to bother you with any dependent event stuff. This is the only kind of dependent event that they are going to give you, because you'll need calculators and stuff or complicated calculators to figure out the other kind of stuff. So with this in mind, let's go ahead and do a practice question. So pause the video now and have a go. All right, let's go through this one together. So we've got a box containing 8 red marbles and blue balls. So 2 balls are drawn at random without replacement. What's the probability that 1 ball is red? So without replacement here is the key. So we've got blue, we've got red. So red here is 8 over 12. There's 12 of them in total, and this is 4 on 12. Blue, red, red. Now, because it's without replacement, the probabilities are going to change. So this one's going to be out of 11. In fact, everything here is going to be out of 11 now. So let's write that in. So if we've picked up a blue, then the number of blue marbles goes down by 1. So this ends up becoming a 3. But the number of red ones don't change. So this still becomes an 8. Now, let's go down to the red node here. So if we picked up a red marble, the number of red marbles goes down by 1. So this becomes a 7. And the number of blue ones doesn't change. So this remains a 4. Now, you can find all of these probabilities if you like, but what's the question asking you? It's asking you, what is the probability that at least 1 ball is red? So we've got red here. We've got red here. We've got blue red here. And this is blue. So the probability of at least 1 ball being red is these 3. So instead of just adding all of those 3 up, why don't we just find 1 minus whatever this is, just to make your life easier. Remember, the game of the UCAT in general is about how quick you can be with everything, not just how accurate you can be. So this helps us be quicker. So 4 on 12, which you can just rewrite to 1 on 3. So 1 on 3 times 3 over 11. You cross out those, you end up getting 1 over 11. That's your probability of getting 2 blues in a row. So 1 minus 1 on 11 is going to be our answer for at least 1 ball is red, which gives us 10 over 11, or our answer of B in this case. So hopefully this example illustrates to you. Oh, sorry, I just realized my head covered this. I mean, if you didn't already hear it, there you go. But hopefully this example illustrates how to actually put these without replacement tree diagrams into practice. So here are some common traps that I see students falling into when it comes to probability. Number 1 is switching between success and failure mid-question for the comparison questions. Number 2 is not converting everything to a common format. And number 3 is avoiding these tree diagrams and trying to juggle multi-step probability in your head. So draw them out. It's going to make your life so much easier. So here are your do's and don'ts. Do convert all probabilities into the same form, decimal and success rate. Do draw tree diagrams for multi-step probability questions, and do remember the principle of independent events. You can multiply the events together, or the probabilities of them, to find the probability of them happening at the same time. Don't let wording like fails 40% of the time trick you into flipping numbers incorrectly. Don't try to mentally track multiple steps. Offload it into a table or a tree. And don't memorize 10 different types of probability questions when really you just need to know the singular principle of independent events. So here's your next step. For the next 10 probability questions, depending on what question it is, then use the methods that we've outlined today. For comparison questions, use the TFS method. That's table, focus on one outcome, and standardize the numbers. For the general questions, remember the overarching principle, independent events. So best of luck with your practice, everyone.